Okay.
Join audio.
Yes, audio is.
Yes.
Okay, it works now.
It works now? Great. Two very broad topics that I spend a lot of my time working on today, but I won't be talking about. One of them is the theory of deep learning. I have the luxury to be working with a very large team on this NSF Simons Foundation project on the theory of deep learning, where we're working on various areas. My own research there focuses a lot on non-convex optimization, global optimality, understanding the over-parameterized regime, as well as understanding deep learning heuristics like dropout, implicit bias, many of those great topics in deep learning. I also work a lot in biomedical applications, and throughout the day, happy to talk about any of them with those that work in those areas. For instance, with Jeff, we share a lot of interest in inverse problems and MRI and whatnot. But today, I'll be talking about a very different topic that I think is becoming increasingly important. And I should mention that this is in collaboration with many colleagues at Johns Hopkins, but particularly my student Aditya is the leader behind all of what I'm going to be talking today. So don't need to tell you that deep learning is working really great for many things. But as it begins working for things that impact people, like self-driving cars or deciding on a credit score, or maybe AI in medicine, it's becoming increasingly important to understand what is it that deep learning does, when it works, when it fails, and why. And so this question of making explanations for the behavior of deep learning systems has become increasingly important. When we look at the history of machine learning methods, it's sort of kind of clear that there needs to be some trade-off between explainability and accuracy. In a certain sense, the simplest way I convince myself, it's really like optimization subject to constraints. As soon as you put a constraint, right, then you cannot maximize your objective as much. And so the way I see it really is that we need to be doing learning subject to constraints on explainability, robustness, fairness, stability, and whatnot. And so that's one of them, interpretability. And so we are, if you wish, at the top left, where we have deep networks that are very, very accurate, but they're completely unexplainable. We really don't understand what the layers do. At the other end, we could go to artificial intelligence in the 1950s, where everything was based on rules that were based on logic. So every rule was highly interpretable, but obviously there was a reason why we're not doing AI with logic rules today. And so a good trade-off, like when we do linear regression, sparse regression, methods that are very popular, we always say, you know, they're interpretable because we are doing linear regression, or we're doing sparse, and so we know what the features are. I am going to say that, well, they're interpretable because we know the meaning of those features, but not because sparse PCA or sparse regression is interpretable on its own right. If those features were the output of a deep network and then we do sparse regression on them, they would not be interpretable. Similarly, people suggest that decision trees are the way to go. They're highly interpretable because they provide a tree of how you make the decision. And the reality is that if you actually take a decision tree, it's, you know, as in the diagram before, it's not going to do so well. And so people say, well, I'm going to do a deep decision tree where the decision at every node is with a deep network. And now they work well. And so once, let's say, you train a deep decision tree for this task, which is to classify birds in images, and you just pick, say, the first root node. And if it is above a threshold, you go one way. If it is below a threshold, you go the other way. And then you say, what images pass the threshold? And can I interpret? Is there a pattern that tells me that these images of these birds are different from those, so that I can actually interpret why this deep decision tree made that decision? And the reality is that they are not. And so the point is that interpretability and explainability isn't because I just put together some mathematical method. There is in order for this to be interpretable, every query at every node of the tree needs to be interpretable. The same as the example with sparsing. So because we care so much about accuracy, the way in which explainability is being done today is, let's just try to be on the far left. Deep networks are very accurate. So let's just try to figure out what is it that they're doing. And the way in which this is done, for example, let's say this is an MRI scan, a deep network predicts that the patient has Alzheimer's with 96% probability. What is done, of course, there are many variants, and I'm oversimplifying the literature here, but by and large, what it's done is take the prediction, in this case, Alzheimer's, let's say Alzheimer's versus not, and 1 or 0. Take the derivative of that prediction with respect to the input image, and then highlight pixels where that derivative is high. And that's what the red regions show, and blue regions means that the derivative. So it's sort of a sensitivity measure. And then you ask radiologists whether those regions make sense or not. And you just begin with this uninterpretable debate as to whether these features or these regions in the image made sense or not, and why. So the good is you preserve accuracy, but the bad is that I think this is just the wrong approach. The explanations are unreliable. We end up debating as to why this is a good explanation or not. And in fact, salient parts of an image might not be necessarily the right vocabulary to do explanations. So what is even more extreme is that there are many colleagues who are really advocating much more strongly than I have done, that basically this is just not the way to go. I like this quote at the bottom, particularly for medicine, that says that the precarious state of interpretable deep learning is such that we should be far more scared upon hearing that a hospital or government deploys any such technique than upon hearing that we have it. So what do we do about it? What we're proposing is that we need to do things backwards. Namely, we need to think about what explainability means in the first place and design systems that satisfies that. In other words, let's just be engineers. We first put down the specifications, and then we design systems that satisfy the specifications. And the issue I have with the current literature is that every paper proposes a way to do explainability, but that's their definition, right? As opposed to we first come up with a definition that might not be perfect, but then the algorithms are all compared against that definition, right? Which is, I think, the way in which you do science. So how do we do this by design? I don't think as a community, we are going to have a definition yet. For robustness, it's a little bit closer to math, and you can talk about what robustness means and Lipschitz constants and whatnot. But for explainability, it might take us another 10 years to come up with a definition. But I like to postulate that the user needs to be at the center. We are explaining this to the user. And the user typically understands explanations in terms of words and symbols, not in terms of an AI construct of, say, sparsity, if you wish, or decision trees. So what the user would like to have is a reasoning that led to that decision. The explanations are not unique. They are actually user dependent. So suppose that I am a clinician and I'm trying to explain a diagnosis to a patient. I'll use some vocabulary, but I will not explain it in the same way if I'm explaining it to another colleague who is also a clinician, because I know that the other person is an expert. So I'll adapt my explanations to the user with a slightly different vocabulary, even though it's the same patient, same diagnostics, same data based on which I'm producing that explanation. The same thing is true when we're giving talks, right? I'll probably try to adjust to the audience. If you ask me a question, I'll figure out, oh, this guy is really an expert. I need to beef up my explanation. Or, okay, probably I did a poor job at explaining it. I have to be a little bit clearer in what I said, right? Because we didn't get it. Naturally, I think the explanations depend on the task. We're going to use a different vocabulary. They depend on the domain. If I am using different data for the same task, I will use a different explanation. Okay, but this still seems a little bit esoteric. It seems like a bunch of requirements for the engineer. So how could we do this? How could we operationalize this so that we can begin making a formulation for it? So what we're going to assume, and I'll be relaxing you that at the end of the talk, but for the time being, I'm going to assume that the user gives me a list of questions that are interpretable to the user. Okay. In other words, what does explainability mean in this framework is, if you, let's say, if I was the AI system and you're trying to get me to explain your things, you can ask me any question you want. If I answer it to you, then you're going to be eventually satisfied, right? That's sort of the idea. There is a query set, and the AI system is supposed to answer those questions. And there, what is an explanation then for a prediction? The explanation is going to be a sequence of questions and answers. And so what are those possible questions for many applications? In the bird classification example that I mentioned earlier, I'm no bird expert by any means. And in fact, if you show me a bird, I have no clue what bird it is. But the experts typically look at attributes. Is the belly yellow? Is the beak elongated? Things like that. And they have on the order of 300 attributes. And what is very cool is that they don't need the 300 to tell you what a bird is. They'll typically just pick 5 or 6 or 7, and they tell you what the class is, just based on the attributes that are present. The second example, for those of you who work in computer vision and want to do scene interpretation, captioning, and whatnot, at this point in time, object detectors are working fairly well, reasonably well. So the idea that you could have a question such as, is there a person in this red window? And now for each object class and every window, you have the cross product can be thousands or maybe 10,000 queries already, just by definition. And you can answer them by just running a detector. Same thing for the attributes. You just can predict attributes if you have training data, of course. For documents, okay, this is passé and old-fashioned at this point to use the queries just being the words, right? Today, you would actually use queries and you'd ask ChatGPT to answer the questions for you, but that's another example. But for medical diagnosis, you can ask the patient the symptoms, or they can be tests and the results of the test. So you just have one symptom at a time and one test at a time, and eventually, based on those, you make a prediction. And that's why medicine is, as far as possible, explainable, because you make that diagnosis because the patient had all of these symptoms. And so for concreteness, in the first example, this is what an explanation therefore looks like. This is, by the way, a result of our algorithm. And the algorithm predicted that for this image on the left, the class is a green jay with 99% probability. And when you ask the algorithm, why did you predict this is a green jay? We can tell you it's because of these 7 reasons. Okay. And these are the queries that were selected. In this particular case, as I said, there are 312 possible attributes. The algorithm selected 7. And there are about 200 classes. So getting it with, this is a great result for this particular image that is with such a level of confidence. If you're curious, the accuracy is on the order of 70%, right, for the task, even though it's 200 classes. All right, so that's the explanation. So in summary, the ingredients is give me a query set, have or train some system that answers the queries. And the core methodology that I'll be presenting is how do I select 1, 2, 3, 4, 5, 7 and get high accuracy at the prediction at the end. Okay. Questions? That's the motivation. That's why I'm telling you all the details in a moment.
So can I ask that looks a lot like a decision tree, right? Does it have this? Does it have that?
Yes, but you will appreciate the difference. So first, yes, it will be a decision tree. Once you get the technique, you'll see it's a decision tree that is built on the fly and conditioned on the input. So it becomes a conditional decision tree that changes for every possible input. Okay, so how do we define and answer the queries? For all of the examples I'll present today, is the examples I already gave you. The queries, you more or less have them, you can answer them. In fact, you might say I'm going to be cheating because you can answer those questions with a deep network that is uninterpretable, and I'm going to be okay with that. Why? Because when we humans talk and explain things, we pick the level of semantic resolution at which we want to explain. We don't tell you that this object is of this class because it has the edges oriented this way and this weird pattern, right? We reason at the level of parts and we're not. And so going from the raw image to parts and attributes, it's okay to be unexplainable in the middle because that's not the right level at which explanations will occur. So in other words, you need to first pick, and the selection of the query set somehow gives you the right level of semantic resolution at which you want to explain. And therefore, not every layer needs to be explainable. All I'm advocating is you must have one layer there that is explainable, and you must make your predictions from that layer as opposed to from all the others. But future work, and I'll touch upon that briefly at the end, is we are working, our next paper will be on how do we automatically get the queries, and naturally it's all with ChatGPT doing it behind the hood.
In
Yes.
high stakes applications, though, you may really need to know explanations at every level of granularity.
Yes. Biology would be one case. Medicine, yeah, it depends. But the main point, and this is the challenge on learning the query set, is you need a query set that has queries at every semantic resolution that is relevant for your task. And in certain ways, what we are saying is that the query set defines the task. Because if you had a query set that is very small, then you can only do so much. If your query set is very rich, you can solve more and more tasks. The other principle is Occam's razor. We want this approach to select the small number of queries because to be general, we can have 1 million queries, but I just want queries. I want explanations that have 3, 4, 5, 10 maybe. Yes.
So then also is the data that you have that you're going to train on, it's going to be like image, label, and query
Yes.
answers.
Yes.
Queries and answers.
Yes.
Got it.
Yes. So the framework, and this framework is actually very old, it's from the 1960s, although the implementation with deep generative models and the kinds of things we do today is very different from what it was in the 1960s. But the core ideas are really old. It's active testing, if you wish, so information pursuit. We're just going to select one question at a time in order of information gain. So, you know, a lot of the things that bother me about explanations in terms of which regions of the image are more important, which regions you pay most attention to, it's all sort of subjective. Here, we're going to have a rigorous criteria. It's going to be, even if you choose pixels as the basis for explanations, it's going to be the pixels that maximize the mutual information for the prediction task that I have in mind. So it's really, by most informative, I mean most informative. And this is going to bring connections with information theory. And in particular, we claim that this provides a basis for a new definition of information, which is semantic. So we're going to think of these queries, which if they're binaries, queries, as semantic bits. We're going to think of the sequence of questions and answers as your semantic code. And we're going to think of the expected number of questions, like how many questions do I need to answer before you get the prediction right? That's going to be your semantic entropy. And therefore, this could be a notion also for task complexity, because if the task is harder, I need to answer more questions before I get there. And so that's the connections with information theory, and I'll highlight a few of those moving forward. So I'll begin the technical part now, tell you what semantic bits are, all of these 3 notions I just mentioned, tell you about the information pursuit algorithm for computing, and how we implement it using sort of modern deep generative model style techniques. And then I'll go through a series of examples, starting with the trivial mnist style, going into the bird example that I just talked about, the text example, and conclude with the medical diagnosis that I already mentioned. All right. So let's begin with a little bit of the notation. So capital Q is going to be the set of all possible queries, and they define the task because if I answer all of the queries, that should be what defines the task. X is going to denote a random variable for my input data. So think about an image that is going to be fed to the system, and Q of X is there for the answers to the queries. And at this point, I'm assuming that they're binary. They don't need to be, but for the sake of simplicity, I'm assuming therefore that Q of X is a million dimensional vector, if you wish, of zeros and ones that has the answers to each one of the questions about that X. We are going to make the assumption. How do we formalize the assumption that the query set defines the task? And what is the task? The task in statistical learning is always to predict the posterior, to make a prediction of Y, which is the target variable, given X, which is your input variable. And this is the key assumption. We are going to make the assumption that the prediction of Y given X, I can completely throw away X. I don't need to know that input image. All I need to know is the sequence of questions and answers for that input image. And so that's why the predictions are just based on the questions and answer for that image. And that's exactly what this fancy notation is that the prediction given X is the same as the prediction given any X prime that has the same answers to X. And so this, in a sense, actually partitions the input space into a collection of equivalent classes, namely all of the images for which the 300 attributes are the same. Okay. So that's our notion of sufficiency. So in other words, if you're more of a statistician, this is simply saying that the questions and answers are sufficient statistics for the task. And so I already said this, we think of each query as a basic unit of semantic information. So it's a semantic bit. And this sequence of questions that I'm going to be asking defines the code. The notation here is, what is the code? Well, obviously it depends on the query set. Depends. But there is this E that is going to be explained in the next slide, which is I need an algorithm, right? I need an algorithm that, given the input X, it tells me what questions to ask. And that's what, in coding theory, this would be sort of half-point coding, right? We encode the data in order to solve the task of transmission and reconstruction. Right now, we're solving machine learning tasks. So what questions should I ask in order to best predict Y? That's what the encoder is supposed to do. So that's exactly what's done here in the picture. I have an input image. I have an encoder that selects what questions I'm going to ask about X. The white ones are the few that get selected. Everything else is not selected. And then the decoder, or the semantic decoder in generalizing information theory, is just going to look at those 5 questions and answers and make a prediction about Y. Okay? That's sort of the notation. So this leads us to our first definition. How do we find that algorithm? How do we find that optimal encoder that tells us what questions to ask? Right? What we say here is that we're going to take the code. The code is the sequence of questions and answers. That bar here simply means number. It's the cardinality of the set. So this bar, blah, blah, blah here is nothing but just the number of questions that I ask. And this is now expected value with respect to X, with respect to all possible inputs. And so what we want to do is select the encoder that minimizes the expected code length. Right? So a very classical notion in information theory. So this is our notion of minimality, of Occam's razor, which is make a prediction by asking the smallest number of questions on average for all input images. That's what it says. And that's what we call semantic entropy, right? And the motivation is really very much related to the classical definition of entropy, that is the expected code related to the expected code length. So hopefully that's clear. The objective is select the algorithm that on average is going to give you the smallest number of questions, subject to that sufficiency constraint that tells you that you want to predict Y, right? So, and so you want the code to be sufficient for predicting Y. And so that's, I think, captures exactly what I said, is select a small number of questions that are sufficient for making a prediction. Now, this all looks nice and connects well with information theory, but the question is it easy to compute? I'm going to have a section on that in a few slides. But for those of you who are more closer to information theory, you might wonder, hey, okay, how does this connect with the things I know? Are there any cases where this becomes the entropy that I know? And so here are a few obvious examples. If what you're trying to predict, y, is equal to x, that's a reconstruction task, right? I give an x, I want to compress it, and then I want to predict, reconstruct it. Then the semantic, and you're allowed to ask any binary query about x. Then the semantic entropy of x and y is the same thing as the entropy of y. So that's one example where we recover classical entropy. Another is, for those of you who are familiar with the 1950s, Shannon's, this expected code length was proven to be within 1 bit of entropy. So we have an analogous result that says that if y is a function of x, then this expected code length, the optimal, right? That's why there is the E star there, is within 1 bit of entropy. Okay. And last property here is the first two are sort of basic. It's semantic entropy. It's non-negative. Is 0 if and only if the two variables are independent from each other. And the last one, I think, I conjecture will have or will be the basis to begin thinking about task complexity, because this is saying, oh, if I use this query set to now solve 2 tasks, say diagnose 2 diseases or classify dogs and cats instead of just birds. The semantic entropy of both tasks together is bounded above by the sum of the semantic entropies of the individual tasks. Again, sort of explaining or motivating why multitask learning, it's a good thing to do, because you share some of the structure. You share the same questions to answer. Okay, I'll skip these learning theoretic aspects, but we are connecting this with VC dimension and extensions of that to sort of suggest that semantic entropy is going to be a good replacement for doing some generalization bounds, but that requires a lot more technicality. So let me skip that. Okay, good. So far I have a definition. It seems to have some nice properties. It seems to make sense, but that's just a definition on slides. What do we do with it? How do we compute? So the challenge is that this definition is intractable to compute, right? Finding the optimal encoder that would always tell you what you would expect that, right? We say in research that half of your success in academia is asking the right questions. The others, once you have the path, then solving the problems is actually way easier than asking the right questions. So asking the right questions is hard. But we want to be efficient by exploiting 2 things. The first thing is that we expect this number of questions to be small. Even though I might have millions of questions, I expect it to be 5, 6, 7, a small number. And so the way we do it is by doing it in a greedy manner with this algorithm from the 1960s. And before I go into the details, I'll just say I have a 10-year-old and I play with him. And so I tell him, hey, I have a number in my head from 1 to 10. Ask me a question. And he said, is it less than 5? And I asked him, why did you ask me if it is less than 5? He didn't quite answer this way, but this is essentially what he said, because I partitioned the space half and half, right? And so that first question that you ask, you have no clue what number I have in my head. You just ask it. Once I tell you, yes, it's less than 5, your next question is going to be, is it less than 2.5? Again, because you partitioned the space half and half, right? And so the second question depends on the first answer, but the first question doesn't. So that's exactly the same principle we're trying to do here. So Q, little q is just one question. Capital X is my random variable, they input the image. So Q of X is the answer. And I'm trying to maximize the mutual information between the answer to that first query and Y, which is what I want to predict. And I select the most informative one. If you're more familiar with PCA, right, this is the first principal component. But you're selecting here the most informative question. I want to emphasize that that first question which might be which region of the image to look at first. You've not seen the image yet. It's purely a property of the distribution, because obviously you're beginning to get into Laura's question. To compute this darn quantity here, you need the joint distribution of answers and the target variable y to compute the most informative one. And so this is a property of the joint distribution of inputs and outputs. And you can select, just if you had a generative model, you could select the most informative. So that's the first one. The second one is the same principle. You always select the question that is the most informative one. The only thing that changes is that now you condition on the fact that you know the exact answer. So that's why there is this little x versus the capital X. My statistician friends tell me that capital X are random variables, little x are the values. So the little x is the image that I get to observe. And so for that, I have an answer for that specific image, while the capital X here is the random variable. And so again, if you're a PCA guy, this is your second principal component, and you know that it needs to be orthogonal to the first, right? So that's what the conditioning tells you. And so on and so forth, right? And you keep asking your questions. When do you stop? You stop when you know that all of the other questions are irrelevant. They don't give you any more information. So if the mutual information of all remaining questions is given the questions I have thus far is 0, that's when you stop. And so that's why you can do it. Now, of course, this is again in theory, but in practice, you can immediately begin to say, oh, well, I'm going to stop when the mutual information is below a threshold, like we do in PCA, right? Things like that. So, okay, we've had all of these papers. Greedy is good in sparsity and compressed sense. This is the greedy procedure, right? The encoder could have, once I give you the 10 most informative questions, there is not necessarily, I mean, the prediction is based on the 10 of them. You don't worry about which order they came about. So why should I do one at a time? It might be suboptimal. For that game that I play with my son, it's been proven that that's the optimal strategy, because in that case, you can always partition things half and half all the time. But in general, there's also a lot of theory from the 80s and 90s that this strategy could be terrible. Okay. Far from optimal. So I don't have the slides, and this is a paper under submission at COLT. But what we have proven in that COLT paper is that what matters is to have questions that are nearly 50-50. If at any point of the algorithm, there always is a question that is within epsilon of having probability equal to 0.5, probability 1, sorry. So if the question is nearly 50-50 with some epsilon, the number of questions you need to ask is something like the entropy of y divided by some function of epsilon. Okay. So roughly the entropy of y determines how many questions you need to ask if you have the ideal query set. And this is going to become important in applications, because if you pick a poor query set, you're going to be asking many more questions. But again, if you ask the right, if you have a continuous battery of all possible queries you can ask, then you could do a pretty good job. Yes.
So are you saying that, like, if this query was like the root of the tree, it should have a 50-50 probability, or at any point in the tree, it should have a 50-50 probability?
At any point. So the probability that Q of X is equal to 1, given the answers thus far, is within epsilon of 0.5.
So how can you guarantee that a query will have a 50-50 probability for any possible tree that you build?
Want to come work with me and answer the question? Yes, we do have some examples in the paper, but that remains a hard question. But my computer science answer is we're going to let ChatGPT get us more questions. Because, in fact, we're doing that right now. I was going to say that at the end. It's like, what are the 300 most important visual attributes of birds? And ChatGPT will answer that question. And you can just concatenate, and with a bunch of prompts, you can get more and more questions all the time.
How is this related to algorithms for learning, like generalized binary search?
It is. It's very related. That's the basic principle. The main difference is simply the following. What is the criteria that you use? So in this case, it's information gain, but that was also proposed. I think this is one paper from '96. The main challenge is that this algorithm is actually super simple and intuitive. So the question again is, how do you implement this? Because if you read the cover book on information theory, we've known what mutual information means for forever. But they never told us in that book that it was not computable when X is an image with 10 million pixels, right? So the whole game is really a computational game. It's like, to implement this, you need to do a lot of work. And that's what the next slides are going to be about. Okay, that being said, in addition to the near 50-50 queries, at least in some settings, we can prove that this greedy method, it's close to the optimum. So within 1 bit, actually. Okay, so continuing to computation. In order to implement this program, we need to compute mutual information between queries and the target variable y. To do that, we go by the cover book. We need the joint distribution of query answers and y. Moreover, because that's only for the first question, for the second question, I need the conditional distribution. So if you're a generative modeling guy, then I need to learn one generative model for each possible history of questions and answers. That's how challenging this is in principle. But make it worse. Learning models with conditions is incredibly challenging because you very quickly run out of data to train them. Why? So let's say mnist digits, and you just want to generate, train your diffusion model to generate mnist digits. Suppose that I tell you, I want you to generate mnist digits conditioned on the fact that pixel 10,15 is black. Of the 80,000 training images, only a subset of those has the pixel 10,15 black. Once I put 2 conditions and 3 conditions and 4, eventually you're just going to have 1 image to train these generative models. Right? Eventually, you have none. Right? So we need the joint distribution. As histories get longer, we run out of samples. Extremely hard to, even if you actually learn the generative model for very high dimensional spaces, how many samples do I need to, mutual information is an expectation. The typical thing you do is you sample and you average. How many samples do I need? Am I sampling well? How do I sample from deep generative models in a way that I get fair samples? All of those things need to be addressed. Yes.
Is one naive thing the data augmentation type of approach? So I mean, I think for at least you, certainly for that pixel being black, you can then just shift things so that pixel is black. I mean, using things we know that we wanted to be shift invariant. So is that one sort of first naive thing to try, or?
Yes, but I think I conjecture the number of training examples sort of reduces exponentially by every condition, and you can never compensate by data augmentation because the amount of data augmentation grows. Okay, I'm inventing this comparison here, but let's say the data augmentation grows linearly and the data reduction is exponential, so you can never compensate. Okay, I really want to show you the examples and the experiments, so I'm gonna go faster on this, but let me just give you the gist. To make this thing work, despite all of these challenges, you need to make assumptions. The extreme assumption you could make is all of the queries are independent from each other. Then you will get very simple and nice generative models and you could learn them. But obviously that's a very bad assumption. What people have done in the past is to assume that the queries are independent given the class, given y. That's a better assumption, but it's still bad. The example I always give is the intensity of this pixel and the intensity of this pixel, are they independent just because you know my identity? The answer is no, that's a bad assumption. What is a reasonable assumption is that they're independent condition in that example. If you knew the light, if you knew the pose, if you condition on a bunch of other variables, then those 2 pixels become independent. So that's exactly what we do here, which we assume that they're conditionally independent, but given some latent variable that I don't know. I am not going to have the time to explain, but for those of you who work on deep generative models, one example that fits perfectly and your latent variable is exactly the nuisance factors and allow you to do this in a tractable manner is to use VAs. Just leave it there. The main point at this point, if you don't work in this area, simply say there is some deep network that gets trained, and that with that, you actually have access to the joint distributions that you want to compute mutual information, and they can be trained more efficiently in addressing many of the challenges that I was talking about. Okay, let me get really to a few of the examples. I'll begin with the mnist digit example that my colleague Rachleff said should be banned from computer vision because we get 99.9999, so we shouldn't use it anymore. But I hope you appreciate that despite that, I'm going to classify it in a very different way that you've never seen, because I'm not going to give you the image. All I'm going to tell you is ask me a question about the image. In this case, we could have chosen the questions to be give me a one pixel at a time. But we did it with all cases with 2x2, 3x3, 4x4. For the purpose, you can see the results in the paper. For the purpose of this talk, I'm going to ask 3x3 patches. So it's like asking 9 questions at a time instead of asking 1 question at a time. And because the images are binary, I'm just asking whether the pixels are 0 or 1. So therefore, the game is going to be select a patch and try to predict the class only from that patch. Select the second patch, and then how many patches you think you need to get the mnist. So I'm going to show you a running example. So this is the true image on the left, is the image of a 2. This is what you've seen thus far. So it's all gray, you've seen nothing. This is your current prediction of what the digit is. You've not seen anything at all. So it's 1/10, I have 10 classes. I know nothing. So now we train a deep generative model to generate images of mnist. Once we have it, we can compute the mutual information between a 3x3 patch and the class. And we can select the 3x3 patch that maximizes that mutual information. So which one is the most informative patch of the image? What would you guess? Would you say that is the one at the bottom left? Who raises their hand for the bottom left? Why is not informative? Because I know it's black. And so remember my 50-50? I know the answer. It's not 50-50 answer. So the regions that are obviously black, the regions that are obviously white are not. It's the ones that are the most uncertain, the ones that you've got to pick. And so it's got to be somewhere in the middle of the image, but it's not actually at the center. It's here, so that's the most informative patch for the mnist data set. And now you can see that this distribution begins to change. Now the algorithm thinks it's probably a 0 or a 2, maybe a 6, maybe an 8. Some other digits go a little bit down. But still, we are not very certain. We are in the 0.2 probability, maybe instead of 0.1. This is the second patch that gets selected. And now the algorithm is a little bit more confident that it's a 2. Then you keep going with the sequence of pixels that get selected. Now the algorithm actually shifts its opinion, thinks that it's probably a 1. You can probably see that a 1 is also consistent with those regions being white. Again, thinks that it's a 1. Now it thinks that it's a 0, and it's becoming sort of confident. Maybe this is like 0.5 chance. And a 0 actually could still be right. So if you think about the most likely chances, obviously 2 is one of them, which is the true one, but a 0 could still be, right? And still a 0. It's only after the 8th question that it became more confident that it's a 2. Because now it cannot be a 0, right? It's a and how do you choose these questions? You want to choose questions that are most discriminating, right? Which patch is going to tell me? If I have 2 competing options, I should choose the patch that disambiguates between those 2. That's the main point. And so now it's probably 0.8, 0.9, 11 questions. It got it right. So that's the fraction of the image you need to look at to make the prediction. You don't need to look at the whole image. And now you could tell me, well, obviously, trade-off. You have to do less than 99.99, because if you do 99.99, you have access to the whole image, you train your deep network for classification, you use all the bells and whistles. Here, we're not. So it turns out that on average, over the entire mnist data set, you need to ask about 11 3x3 patches, and you get 99.15 accuracy. So I'm sorry we lost that 1%. But that's because now you produce an explanation. I tell you what is the sequence of pixels I looked at. And I have a criteria for choosing them, which is really the most informative for that task. Whether that's an explanation, I argue no, but if you believe that looking at pixels and patches is the right explanation, then the framework applies to that as a particular case. The other thing is that you can now take more data sets that are a little bit more complex. And as I had suggested or hinted, the number of questions is more. Okay, the bird example, just one example here, but we did it for all images, so we have the results for all of them. It's the same idea. First question is the shape Pershing-like. Green means yes. Upper parts color yellow. Red means no. But the belly color is yellow, but the upper part is not. Okay. And 1, 2, 3, 4, 5. After 5 questions, by the way, I'm not showing the 200 classes here. I'm only showing 10. Okay. But after 5 questions is picked on 4 possibilities, then 2 possibilities. And after 7 questions, it just picked to 1, which is the correct one, which is that it's a great crested flycatcher. I shortened the presentation, but if you ask the question, if you train a deep network to do this task, what's the accuracy? I think it's 82. What can we do with this framework? We lose like 5 points. Okay. And so we don't get as much, but then now it's fully explainable. I can tell you the 9 reasons why this bird was classified as such. Yes.
I'm just trying to understand. So like in the Digis example, are you training a classifier to predict the label from each patch?
From the sequence of patches thus far.
The sequence, okay. So to find the first patch, you look at all 3x3 patches and
select the one that has highest mutual information.
and how do you determine that? I mean, mutual information, I think of this between 2 main variables of the same dimension. So are you?
So Q of X, no, it's mutual information is between 2 random variables.
Okay.
And so Q of X is the Bernoulli variable as to whether the pixel is black or white. And Y is the label.
But if it's a patch, what's?
If it is a patch, then it's the joint mutual information of the 9 variables together.
Okay.
With the label. So it's a 9-dimensional binary vector with a label that is a 10-dimensional
Okay.
binary vector.
All right. So if it's bigger, you need a lot more samples from your generative model to get a good estimate.
Yes.
Right. Okay.
Yes. Yes, you need to sample again. So I will address it in 1 minute at the end, but the bad of all of this is that it takes forever to compute all of this, right? And so our iClear paper solves all of those issues. So I'm telling you the TPAMI paper, December 2022.
Okay.
The iClear, which is next month, has addressed all of those. I'll tell you that at the end. Okay, briefly here, because this provides an example of choosing a bad query set. Here, the task is find the category of the document. Again, there are like hundreds of categories. Travel is one of them. Based on this text, there is typically a headline and a short description. We chose the presence or absence of a word as our query set in this particular case. And what happened? Okay, we trained the model on the Huffington Post. There are 100,000 documents, whatever. We do all of that generative modeling that I talked about with this data now. And we compute mutual information. It turns out that the most informative query is whether the word Trump is present or not. What is interesting, you look 1, 2, 3, 7, the answers are no. And the main difference I hope you appreciate it, took us 125 questions to stop. So it's much longer than before. And why is that? Well, whether a word is present or not in the document, by and large, is all with higher probabilities no than is yes. So these are not 50-50 questions. So that gives you an example of how you choose a bad query set. The algorithm is just going to take longer. It's going to get there, but it's going to take longer. And so that highlights the importance of choosing a good query set. So that's why I wanted to mention this example. And this, I'm not going to go through it again, just the high level details, but this is the medical diagnosis based on symptoms. There is this SIMCAT data set, 200 data set that has 200 diseases. For each patient, you have a sequence of symptoms. It's very sparse in general. And again, we've been able to build a classifier for diagnosis that is, maybe I'm going to show the last slide to show you how better it is than the state of the art. So the last comment I simply wanted to make, how does this compare to other things that you might have imagined doing? And so the comparison here is the x-axis is how many questions do you ask, and the y-axis is the accuracy. And these three different plots have three different data sets. So let me concentrate on the simplest, CFAR10. You're trying to classify CFAR10, and you are asking how many questions do I need to ask? You could say, hey, just randomly select the questions. How bad, and then just use the optimal encoder that we have learned with our framework. How badly are you going to do? So that's the green curve. It's called random, and it's kind of in the middle. You could, if you're a reinforcement learning guy, say, this idea of selecting the next question is like taking an action. The idea of classifying it right is like my reward. The sequence of questions and answers thus far is my state. I can probably do a reinforcement learning approach to just directly predict the next question to be asked. So this is the RAM and the RAM plus methods. They do worse than RAM. And the one that does a little bit better is this orange curve. That is, if you give up on really computing mutual information and you say, I'm going to compute attention maps with transformers, and then so probabilistic hard attention is the orange curve, and the blue curve is what's at the top, which is the information pursuit framework that I talked about today. And same thing is true for all of the other data sets, essentially. Okay. Yes.
How do you explain that reinforcement learning cannot do better than random?
There are a couple of reasons. I'm not a reinforcement learning expert, but I think training reinforcement learning is just generally hard. But there is the question here of delayed reward. You sort of run through all of the queries, and once you're at the end with the full history, you classify. And so the question of how do you adequately define a reward that gives you early feedback? And also, how do you do the reinforcement learning here with the idea that you won't stop as well? Because the idea that you want to do it with a minimum number of questions. So there are a few technicalities that make that you don't have enough rewards early on, and then you have the conflict that you have to stop. And plus the usual issues with reinforcement learning, like you have to get a lot of trajectories as well. Yeah. So the iClear paper, just to tell you in 30 seconds how we can do this in a computationally intractable manner. By the way, all of these experiments are with the iClear paper, not with the generative models, because the generative models, we can only do mnist by and large. And you can classify at 1 mnist digit per second, I think, instead of 1 per millisecond. So it's like 1,000 times worse. This idea of build a generative model, compute the mutual information. It's like you're model-based guys. You just go by the book. But that's a means to an end. That's not the goal. The goal is simply give me the most informative one. And so I don't care to compute mutual information super exactly. I just want to know which one is higher than the other. So it turns out you can train a deep network to select the next query based on a random previous history. And if you train it with KL divergence, you can prove analytically that it gives you the one that maximizes the mutual information. So that's what that IClear paper is about. And now you can do it very fast. You just have a network that, given any history, it will tell you what's the next query to ask. In summary, I hope to have convinced you that, in my opinion, and in the opinion of many others, the way we're doing explainability today is not the right way. That we need to work a lot to agree on a definition of what explainability means first. I've proposed one. I'm not saying that is the right one. And I'm saying that probably will take us 10 more years for the community to come up with the right one. But hopefully it has ingredients that you will appreciate, that it's the right direction to take. And we've gone from the way to do it in an intractable manner to the way to do it in a more efficient way. And the next thing is to enable this. I mean, for every application, it's a new network, a new training, a new query sets, so learning query sets, understanding when a query set is sufficient for a task, the question that you want to work with me when you move to my lab. All of those is future work. Thank you.
So the queries from what you actually showed are kind of like simple queries. Why do you actually need, what is the need for a deep generative network to basically like do that? Have you actually tested it on other networks, or not networks, but then on other models to see if these queries will actually predict the same answers?
Okay.
It can seem to be simple enough to answer. So why a deep network?
You need the question is not, okay, no. There are two independent parts. One is, given the question, how do I answer them? In fact, let's assume for the time being that there is an oracle. Let's say even a human is answering. There is a different question, which is, how do I select what question to ask? And for that is where we needed these generative models and mutual information and a big deep network. That's even if the answers are oracle. In addition, you could say, okay, I don't have the human answering the questions, and I need a shallow, a deep, or whatever model you want to actually produce answer. And then you're doing these 20 questions with noisy answers, as opposed to with oracle. And then you would even have to reason about, do I choose a very informative query that has a very high variance, or do I choose one? So now you begin looking at those trade-offs.
So in some sense, I would say that the queries will actually become harder if you actually move away from a deep network. Like we are basically saying that if you don't have, when you're talking about not having an oracle, right? You're basically saying that you're having noisy models.
Yes.
And so if you have, the more noisy the model gets, the more harder the query becomes.
Interestingly, not necessarily, and at least experimentally, we had these the experiment of birds that I talked about. For that, we had the true annotations from users as to what the attributes are. So we did the experiment. Do we just use those, therefore oracle answers, to run the information pursuit framework and produce that curve of how many questions do I need to ask in order to get some accuracy? Or do I train a deep network to predict the attributes? It turns out that it works better to do it with a deep network that predicts the attributes. Why? It's because during training, if you're training a query to select the next question, at inference time, you want to train with noise in a sense. You want to train with uncertainty as opposed to if that's the way you're going to be tested.
Okay.
Yeah.
That's a fascinating talk. I probably don't fully understand everything, but I wonder if you want to comment on some models like the vision language models, or like the CLEAP type of models, and they learn the representation of an image in terms of semantic attributes. How would this type of methods compare to those kind of models? You know, there are ChatGPT that actually can generate text queries and descriptions of an image, and maybe under the hood, they use some of those multimodal learning framework as well.
Great question. So great that that's exactly the experiments my student was showing me last Friday when I last met with him. So I will precede the answer to your question by saying, well, okay, how do we move forward in the sense of I don't want to have a prefixed query set. I want to leverage language models. Or how do I go from 300 attributes to 1,000,000? The challenge with that bird example is for every attribute, I now need to train a classifier. If I had 1,000,000 attributes, not only I need to train a classifier, I need a notation for those attributes. So your question is dead on in the sense of, oh, but CLIP is a model that was trained to learn a joint space for images and text. And now that I input any new query in language, actually, that I didn't even know what the query was. And I do the dot product with images in the data set. I know I can identify images that have high similarity. I can pretend that maybe the dot product of CLIP embeddings above a threshold is the answer to the question, yes or no. And so we began doing exactly those experiments to assess the performance of CLIP embeddings. And we compare it with the CAP dataset. He was just showing me this last week. And it turns out that with CLIP embeddings, you do, that there is a significant gap. And the reason being, to some extent, CLIP is just trained on some domain, whether I can just use it as is for a new domain. Second, how do I know that it's really answering question, and how do I pick a threshold? So what we got to work nearly close to what we're doing on the CAP data set is to train a VQA system. Like you just consider the CLIP embedding for the image, the CLIP embedding for the question, and now you train it because we have the answer for the CAP data set. So if you actually train it for answering questions, and it actually generalizes to new questions you didn't have in the data set. So I think, long story short, what you're asking is exactly what we're doing. And I think it's going to be the way to scale it to new query sets without having to learn them. And naturally, the interaction between using ChatGPT to get questions in the first place, plus vision language models to answer them is the way to scale. So the next paper. Yes.
Well, I mean, your talk, you said that there's an independence in the latent space. How do you learn the encoder to learn the embedding?
What I said was, we assume that the queries are conditionally independent given the class and given some latent variable. And so when you write the joint distribution of queries and the variable y, you marginalize with respect to the latent variable. And then because you're conditioning on z, you can take the product over the query set. That's what I said. So the queries are conditionally independent. And once you write down this model, essentially, in long story short, this is just the standard thing we do in generative modeling, is that you make some statistical independent assumptions in order to make the learning and inference more tractable. Yes.
Is it required to have like binary questions or answers? Like, is it yes or no question?
No, that's for simplicity of explanation and implementation, but no. And in many of the applications, they're no.
What about real valued?
I have another PhD student working on that. The real valued case is a little challenging, more challenging, because unlike discrete spaces, mutual information can be negative. There is a distribution becomes degenerate. So what I know thus far, which is relatively simple, is that this information pursuit framework for PCA gives you PCA. Like if the query is to do the dot product with a direction, and now you have continuous queries, and to select the most informative query, you optimize over any direction, then you get the first principal component. But that means you assume that it's Gaussian and all those things. We are trying to make connections, say, with orthogonal matching pursuit, where you also select one dictionary atom at a time in a greedy manner, but crafting what the query set is and what mutual information to compute and what is the right generative model for that to happen. The stars have not aligned, and we're still stuck on re-engineering the matching pursuit so that it looks like information pursuit. So we're working, but it's a little, it is harder. So we'll get.
If you succeed in that, I mean, you described at the beginning of your talk, interpretability as sort of things that could be said in words, but dot products with vectors don't sound very word-like, right? So how would you connect it back to your original concept of interpretability?
So in the paper, we put forward 4 types of query sets. Linear classifiers is one of them, the one I just mentioned. And the 4th category is the one that is for the purpose of explainability. So if your take on this is more information theoretic, then there is lots of queries. Some of them are interpretable, some of them are not. And the ones that are not interpretable are useful for many engineering and machine learning tasks, but not for explainability. In order for this to be useful for explainability, then the queries need to be semantic. Dot products still show up because the embedding of a sentence, dot product with the embedding of an image still shows up. So you can.
Questions? No, let's set speaker again.
I didn't know you were expecting.
Al, are you there and you have a question?
Can you hear me? Can you hear me?
You want to say it or type it in the chat?
I'll type it in the chat.
But it was a good time.
Yeah.
June. It's summer.
No, but Al had raised his hand. Al, if you have a question, either say it or type it.
Really appreciate it. Alex, I appreciate it.
Put things together. And I really, I mean, I think